Good day, everybody. Today I want to use differentials to approximate what the change in gravity must be for a given change in a period for a pendulum clock. And this first was realized, well, I think first realized, there were some nice pendulum clocks, grandfather clocks, well, pendulum clocks, made in Europe, and then they would get shipped to America, and they started to run slow. So they would ship them back, and then they would work fine there, and so they didn't know what was going on. There's the article, and I can read it here, but it goes into it. And in the end, well, I mean, it helps to have Newton's law of gravity, and then also realize how latitude would affect the effective rate of gravity. So, long article, we're not going to read this, but I'll have a link to it. So, let's use the differentials. The standard formula for the period of a pendulum is 2 pi square root of L, where L is the length of the pendulum, divided by G, where G is the gravity. And that's technically an approximation. This is more of an exact formula. Now, for what we do, both L will be fixed, right? If you're not changing the length of the pendulum, so L is fixed. And the angle, the max angle alpha, we can kind of consider that fixed. So the period, if you move it around, kind of the only variable would be G, if it's going to swing with the same amplitude. So I'll just use this formula, and we've got these constants here. They cancel out when we do our relative error. Anyway, so the period T is 2 pi square root of L, G to the negative 1/2. Again, L fixed. So the differential dt is 2 pi square root of L, then the derivative here, negative 1/2 G to the negative 3/2 dg. And canceling the 2's, we get this. So if I look at the relative change in period over the period, it'll be dt over t. So I'll just put in that rule for dt over the rule for t. And of course those constants do cancel. We do have an extra 2 that came from the derivative, actually. And so we've got dg, and then these g's simplify to give me just a g in the denominator. So negative dg over 2g. So that's what I have here. So the and then, well, we're using differentials to approximate. So change in period over the total time is going to be negative 1/2 change in Earth's effective gravity divided by Earth's effective gravity. So if I solve for the change in gravity from this equation, it'll be negative 2g times change in period over total time there. And in the article, the clock was losing almost 5 minutes per week. So I went ahead and used 5 minutes per week. So if the clock was slow by 5 minutes per week, notice slow actually means the period's increasing, right? It takes a little longer to go back and forth. That would be the period. So the clock's running slow 5 minutes per week. Then that's 5 minutes, and then this would be the number of minutes in the week. 60 minutes per hour, 24 hours per day, 7 days per week. And that's roughly 5 times 10 to the negative 4, if we want to approximate it. So if I plug that into here, then the change in gravity that there must be, because our clock's running slow by 5 minutes per week, is negative 2g times this 5 minutes per week. Kind of coincidentally still has a 5 there. And multiply the 2 times the 5, to get negative 0.001. And, you know, what's g? Well, g is roughly 10 meters per second squared. So ends up we must have a slightly lower g where the clock's running slow by about 0.01 meters per second squared. And then just to compare what's in the article, actually I decided to solve for that exactly. So let's, instead of solving for delta g, let's solve for delta t, where now I want delta g to be negative 0.01. All right, so I just go back to this equation, and if I solve for uncertainty or the error in the period, well, it's negative delta g over 2g times t. So I want it so that delta g is exactly 0.01 meters per second squared negative. For g, we will use 9.8 meters per second squared. And then I'm going to use how many seconds there are in a day. So 3,600 seconds in an hour, 24 hours in a day. So that's how many seconds there are in a day. So for delta g to be negative 0.01, then how much the clock will run slow, well, it'll be negative of that negative 0.01 over 2g, how many seconds in a day, and we get about 44 seconds per day. And I'm going to compare that to the article. And incidentally, of course, 44 seconds per day times 7 days per week times 1 minute for every 60 seconds means that would be about 5.13 minutes per week, or 5 minutes 8 seconds per week. So 5 minutes per week is about 44 seconds per day, but a little bit more exact there. So back to the article. Just quickly scroll to it somewhere around here. Again, the link will be in the description. There we go. So they give how much the clock will run fast or slow, and for the different g's. So notice these g's are changing by exactly 0.01. So as they go down by 0.01, the period is increasing by exactly 44 seconds per day. So to go from 1 minute 26 seconds to 42 seconds, that's a 44 second difference. And then from 42 seconds fast to 2 seconds slow, that's a 44 second difference. And then 2 seconds slow to 46 seconds slow, again 44 seconds difference. And then another 44 seconds gives me the minute 30. So these were changes in the period by 44 seconds, and that led to changes in g of 0.01. So using differentials, it makes that problem a little easier. So hope you start to see differentials everywhere you go. And rather than being a nightmare, I think it'll be a blessing. Anyway, thanks for watching, and have a good day.